Okay, continuing with our discussion of vectors and planes, this is part 2. So the question comes up, where do these equations of planes come from? How do we know that ax plus by plus cz equals d is a plane, and how did we come up with that? So here's how it looks. If we take any point in the plane, so this parallelogram is supposed to be a plane, kind of like a magic carpet that goes forever. Now imagine that this is a point in the plane A, and then we look at a vector that is perpendicular to the plane itself, and I'm going to call that n. So if a vector an, so we're going to call that vector an, is perpendicular to a plane, then it is perpendicular to all of the vectors in the plane. Then it is perpendicular to all of the vectors in the plane. That kind of takes a moment, I think, to digest. But remember, that vector is movable, so we can slide that around, and any plane that you draw that is completely contained in that, any vector that you draw that's completely contained in that plane is going to be perpendicular to the vector an. So if P is any point in the plane, if P is any point in the plane, then it must be true that vector an is going to be perpendicular to vector AP. And if two vectors are perpendicular, that means that their dot products are going to equal 0. So vector an dotted with vector AP must be equal to 0. This is going to be key. So this right there that I put the box around is a vector equation of the plane. And so we're going to see how do we go from the vector equation to what we're looking for here, this ax plus by plus cz equals d. So let's see what kind of, let's see what kind of Cartesian equation this leads to. What kind of Cartesian equation this leads to. So let's pick, we're going to call A, that point that we have up in our picture there. So we're going to call A, its coordinates are going to be x sub 0, y sub 0, comma, z sub 0. So there's that initial point on our perpendicular vector, sometimes called a normal vector. So this is now going to be fixed. So A, we're going to say, is fixed. We're not choosing it to be anything at all. And it's not going to move around. And then we're going to pick the point P to be, we're going to say P has coordinates x, y, and z. And P is kind of our generic point. So it is any point in the plane. Any point or every point in the plane. So just to visualize it, I'm going to pick P to be over here, and I'm going to label it x, y, z. So there is our point P. And then we know that the vector AP, so vector AP, we know is going to be this tip minus tail. So it's going to be x minus x sub 0. So I'm taking the x coordinate of the P minus the x sub 0 of the A, and y minus y sub 0, and z minus z sub 0. So there is our vector AP. And let's just call vector AN. I think I made that yellow. So I'm going to go AN. Just to make things simple, I'm going to call it's going to be ABC. Those are its components. So it'll be nice and clean. So that's our is a vector, we'll say perpendicular to the plane. So that's its defining characteristic there. So what we know then is that AN, our normal vector or vector perpendicular to the plane, dotted with AP, must be equal to 0. That's what it means. So you can kind of see that if, there's our vector AP and there's our vector AN, no matter where we put P in the plane, it's going to be true that AN dotted with AP is going to be 0. So what that means, let's see, if we take the dot product, we're going to get x minus x sub 0 times A plus B times y minus y sub 0 plus C times Z minus Z sub 0 must be equal to 0. That's what it means for two vectors to be perpendiculars. Their dot product is going to be 0. Well, if we distribute that, we're going to get AX minus AX sub 0 plus BY minus BY sub 0 plus CZ minus CZ sub 0 equals 0. So if we leave the stuff without the minus signs on the left side, we have the AX plus BY plus CZ, and we add those others to the other side, we get AX sub 0 plus BY sub 0 plus CZ sub 0. So this is exactly what we said when our equation of a plane is AX plus BY plus CZ equals D. So remember, these are just going to be numbers here, and now we even know how to come up with that D. The D is actually going to be that A times X sub 0 plus B times Y sub 0 plus C times Z sub 0, where the ABC are coming from our normal vector that we saw over here, and the X sub 0, Y sub 0, Z sub 0 is coming from our point A, that is the base of the initial point of that normal vector. Okay, well this is actually a formula here for coming up with an equation of a plane. So let's look at an example and see what this is going to look like with actual numbers in it. So let's say that our vector perpendicular to the plane, is going to be, we'll call it V, and it's going to be 2, negative 1, 3. And our point A, which is just any, it's going to be the base of that. So A is going to be, A is our point that is on the plane. So that's like our kind of that random XYZ, except it's not the random one, it's just any point that's in the plane. And so A, we're going to say is 4, 3, negative 2 is any point in the plane. So with that, what we can do is we know from our normal vector here, this is going to be our A, B, and C. And we know that the D that we're looking for, this D is going to come from our the 2 from the A times the 4 in that point A, plus negative 1 from our normal vector times 3, which is that y-coordinate of that point in the plane, and then plus 3 times, and then we have a negative 2 is that z-coordinate of that point in the plane. And so that's going to be, it looks like 8 minus 3 minus 6, so that's going to be a negative 1. So that is our value of D. And so that means our equation of the plane is going to be, we're picking out the A, B, and C from our normal vector, that vector V. So it's going to be 2x minus y plus 3z equal to D the negative 1. That's the equation of the plane with normal vector V, that is vector perpendicular to the plane, and the plane that contains this point. Okay, I'm going to go to a new screen here.